the spread that rivals mine.
It's just...
And we're rolling.
Okay, we're going to talk about the first week of X-ray physics. We're going to talk about lecture first, and then a little bit about lab. There's a lot of different sources for all this information on Blackboard. It's tough to sift through. I'm going to try to hit the highlights of the review sheets that she provides for us, because it looks like that's where the majority of the test information is going to come from. So we're just going to kind of go through this real quickly. What is an X-ray? It's electromagnetic radiation. It doesn't have any mass. It travels at the speed of light. Basically it's a stream of photons. Let's see here. Another important thing to know about X-rays is that they're emitted by the electrons outside of the nucleus of an atom, while gamma rays are emitted by the nucleus, and that's a real important distinction that's going to be on the test. Another name for a single X-ray in the beam is photon. And what determines the energy of the X-ray? The only thing that determines the energy of the X-ray is its wavelength, and then obviously, inversely, its frequency. Do all the X-rays in the beam have the same energy? No, they definitely don't. And the reason that we know this is because we get differential absorption. So differential absorption basically is the phenomenon that we recognize. It's what creates the different shading on the film. So if there were no differential absorption, i.e. if all the X-ray beams were the same wavelength and frequency, then we would get a homogeneous image on the film. It would all appear either a certain shade of gray or black or whatever. But it wouldn't show up the way that it does if they were all the same energy. So basically that goes into what differential absorption is. The higher frequency, lower wavelength, the higher wavelength X-rays are able to penetrate the tissues that are being X-rayed and go through and excite the crystals on the cassette, which then puts the image on the film. It shows up as dark, and the lower energy ones are the ones that interact with the atoms that compose the actual thing that you're X-raying, and that's what produces your image. So the low energy waves are the ones that show up as whiter on the film, whereas the higher energy waves pass right through and show up as darkness on the film. Now we're going to talk about radiographic density. Radiographic density is inversely proportional to anatomical density. That's really important to remember. Radiographic density has to do with how dense the image is. So if we're talking about anatomical density, high anatomical density is going to produce lighter color images on the film, whereas radiographic density relates to the density of the X-rays that are actually hitting the film. So high radiographic density equals darkness, high anatomical density equals lightness on the films. So that's how those are related. They're related inversely, remember that term. Radiographic contrast is the degree of density difference between the two areas on a radiograph. So basically what we're talking about is how white is the image in compared to the portion of it next to it that's dark. So we can understand exactly how dense a bone is in relationship to maybe the soft tissues around it or something like that based upon that degree of contrast. The more the contrast, the more the difference in the density. How do we have contrast in an image? How does that happen? I think I basically covered that. It comes back down to kind of a key term that we need to remember, which is differential absorption. Okay, and the differential absorption obviously has to do with what's being absorbed by the anatomy that we're actually X-raying. What would the film look like if all the X-rays interacted with the emulsion and the film was then processed? Well, if all of the X-rays get through and interact, we're talking about the high energy waves, which remember shows up as dark on the film. So the film would be completely black if all of the X-rays were able to pass through the image that we're trying to X-ray, or the structure that we're trying to X-ray. Is it really the X-ray that interacts with the film emulsion to produce the image? We know that that's not true because that's why we use the cassette. The cassette is what has the rare earth salts on it. And so what happens is the X-ray hits the rare earth salts, which causes them to vibrate, and it makes the silver halide crystals that are basically impregnated on the film show up as darkness. Again, that's what happens when it interacts with it. So the X-ray does not interact with the film emulsion. The X-ray interacts with the rare earth salts that are on the cassette, which then interacts with the film emulsion to produce the image. And what color do rare earth crystals typically emit? And that's a green, yellow light. So it's actually the thermal energy is what causes these rare earth crystals to emit that green, yellow light and then implant that image onto the film. Okay. So this is our second review sheet. And I do believe maybe that she's going to get back into this. I can't remember if we actually went over this one or not in class. Okay, describe electromagnetic energy in terms of mass, charge, and velocity. Okay, so it's important to understand that X-rays are just a form of electromagnetic energy, just like a radio wave, a UV wave, and gamma waves also. So it has no mass and it has no charge. And the velocity is the speed of light. So remember that for all electromagnetic radiation. No mass, no charge, traveling at the speed of light always. List the other types of electromagnetic energies in order of their energies relative to X-ray. So this is going to be important. She said that this was going to be on the test. So in order of longest wavelength to shortest, we've got radio and TV waves, microwaves, infrared, visible light, UV light, X-rays, and gamma rays. Another thing that's important to note is that gamma rays and X-rays can have overlapping wavelengths. The main difference between gamma rays and X-rays does not have to do with the wavelengths, it has to do with where that energy is being emitted from. With gamma rays, it's being emitted from the nucleus of the atom, and with X-rays, it's being emitted from the electron cloud of the atom. Define ionization. Ionization is the ability to totally remove an electron from its orbit around a nucleus. And we know that X-rays have a high enough energy, i.e. a short enough wavelength, to be able to do that to an atom, to actually knock an electron out of its cloud and displace it, therefore ionizing it. Which of the types of energies in the electromagnetic spectrum have the ability to ionize? X-rays and gamma waves, and just a few of the shorter wavelength UV waves. That's kind of an afterthought. I'm not sure how important the UV wave portion is to it, but for sure know that gamma rays and X-rays have the ability to ionize or displace an electron. What makes an X-ray photon higher in energy than a microwave? We talked about that. It's all about wavelength. Short wavelength equals high energy. State the wave equation. I found a few different things for this. Some of it was really complicated. I'm pretty sure what the take-home message is with that is that all electromagnetic radiation travels at the speed of light, and so when we multiply the wavelength by the frequency, it always comes out to the same standard, which is 186,000 miles per second, I believe, is what the speed of light is. So the wave equation just basically states that all electromagnetic radiation travels at the speed of light, and wavelength and frequency are inversely proportional, therefore they're always going to multiply to the speed of light. What is a gamma ray? We already talked about that. I think we got that down. Difference between gamma rays and X-rays, we already talked about that. Is a gamma ray always higher in energy than an X-ray? No, it's not, because we just talked about that. They have wavelengths that overlap. So you might have some gamma rays are lower in energy than some X-rays and vice versa. Will you as a chiropractor ever use gamma rays in your practice? I'm 99% sure that no, we won't, because those are the types of radiation that can actually be really, really harmful and can cause cancer and other kinds of problems in the body. Will exposure to X radiation leave matter radioactive? No, it won't. Only gamma radiation will, because as soon as you stop producing X-rays, the damage is essentially done. Everything that's going to happen has already happened as soon as you turn that off. With gamma radiation, that radiation continues to radiate over a period of time and continue to cause damage. The one thing that is a little bit dangerous about the X radiation, obviously, is that it can knock an electron off of its cloud within the body, which therefore can create free radicals, which we all know can be detrimental to health if they're produced in too high a number. Again, the only similarity between X-rays and gamma waves is that they can both ionize. Remember that one. To avoid being exposed to X-rays, how long must you wait before entering the X-ray room after exposure is terminated? X-rays travel at the speed of light, therefore as soon as the X-rays are done being emitted, there's no further, need for any concern because all that radiation has already been delivered and dissipated, and it's safe to go back into the room. And why is a free electron in human tissue a worry? It produces a free radical in the body. X-rays ionize atoms, which leave both an electron and a positive ion. The electron can hook up with water to produce hydrogen peroxide, which we all know is toxic to the body, and your body has to go through an extra couple of steps to be able to neutralize that so that it's not harmful in your body. DNA can also be hit, which is a direct action. Basically that alters its structure, and most of the time all it does is separate the two strands of DNA. Therefore that's not a huge deal because it still leaves an intact template so that you can repair that DNA, and it can still be used for protein synthesis. However, every once in a while you can actually hit the DNA and break it off, therefore possibly even creating a mutation. That's where some of the concern comes in with possibly too much radiation causing cancer and things like that, unchecked cell growth. One thing that she also mentioned was that the alpha particles inhaled in cigarette smoke may actually be the thing that is causing cancer in a lot of lung cancer, smoking-related lung cancer cases. Okay, and real quickly, just a few things about the tube from lab. It's encased in Pyrex, which is heat-resistant glass. The positive electrode is obviously the anode, the negative electrode is the cathode. The difference between the two filaments in the cathode is size. They're made of the same stuff. It's tungsten. Everything is the same except for the size. And the advantage of the small filament is a sharper image. The large filament has a little bit more of a cloudy image. I think the $1 million word there was penumbra. Penumbra is the shadow that is cast on the outside of the image on the film. And the advantage of the large filament is shorter exposure times. The one thing that I know is important is MA and by extension SMA, and then also KVP. I'm a little bit fuzzy on both of those. I need to ask her a little bit more about it. But basically from what I remember is that the MA is the milliamps that is introduced into the coils, the tungsten coils. And so what that does is the higher the milliamps go, the more electrons basically that you get to dissociate from the tungsten wire that then are then directed at the anode to form X-rays. So what happens is as you increase that, the millivolts that are delivered to that, you increase the number of electrons up to a certain point at which it's saturated. It can only lose so many electrons at a time before it can't lose any more electrons. And the amount of electrons that are being generated that are able to basically become dissociated from that tungsten wire is what's known as KVP, and kilovolts peak. And so once you get up to a certain point, peak, it doesn't matter how much more millivolts get in there, you're not going to dissociate any more electrons up to a certain point. And I believe that's all I've got